Can you all hear me? Okay, where's my phone? Hello, everyone. Can you all hear me? How are you all? Good morning. Hi, Saransh. Hello, Aniket. Good to see you here. Awesome. Thank you. I guess we can get started then. So, good morning, everyone. I'm Sai Avinash, and I'm a studies fee at Google Dublin. And in this lecture series, I'm going to be teaching dynamic programming. And I'll be teaching it through solving problems from the Atcoder DP contest. And I'll not just solve the problems. I'll solve a few tiny variations of it and how to optimize your space while doing so as well. Like while for example, there might be cases where you need to reduce the time complexity or the space complexity, not just the time complexity. I would try to approach that too as well. And I would tell you how to approach it as well. And you can apply it to various problems in your drill. So these problems are a small set of frequently occurring problems, you can say, frequently occurring concepts. So I would be discussing each one of them, like most of them actually. That's the plan. And all right, let's get started. I'm a little about me. I'm All India ranked 4 in CodeChef. I'm a 7-star under Atcoder there. My marks rating is International Master at Codeforces. I'm currently a master there, and previously interned at Uber, and I'm also snagged on finalist. The subjects that I take are discrete maths, dynamic programming, graphs, and a lot of other competitive programming topics, including live solving and so on. Use the code SciLife to get a 10% off on the Unacademy Pro subscription. So every Friday night at 10 p.m. we have college projects by Raj Vikramaditya. It's part of Unacademy's career as a developer subscription at only $9.99 per year. So he's going to take your projects and he's going to tell what's missing from it and how you can make it better. Additionally, he can also like suggest which projects you can do to make your like profile look better. So if you think it's going to be useful for you, do subscribe to the Unacademy's career as a developer subscription. So then we have Coach of Apprentice. It's a show every Saturday afternoon at 2 p.m. It starts on 14th August. Well, it's already started and it's taken by me. And in this Coach of Apprentice, I would be taking up a student or any person who's like a bit stuck with competitive programming or in his very start, in his very beginner stage, and I would in his or her beginner stage, and I would like address the blockers or any other help they would need. So if you're a beginner too, there's a chances are it's going to be useful to you because you'd be able to relate the blockers. So do subscribe to this channel. Join the channel on Telegram. Like here's the link in the description as well, to get live updates on the latest videos and so on, so that you don't miss out on any of them. So if you think you found this content useful so far, do drop a like so I know it is, or you can drop a like at the end of the video if you think it's useful. And if you think your friends are just starting off with competitive programming and are looking for a resource to learn, or do let them know about this channel and ask them to check it out. It might be useful for them. And if you don't want to miss out on any of the the latest videos which are educational videos, do subscribe it. Right, let's get started with the problem solving without any more delay. Yeah, awesome. So what do we have here? The name of the problem is grid 1, and let's take a look of how the problem is. One second. Okay, so here's the problem. There is a grid. Let's read the problem first. So there's a grid with h horizontal rows and w vertical columns. Let I, j denote the ith row from the top and jth row from the left. For each I and j, square I, j is described by character aij. If that character is dot, it means it's an empty square. If it's a hash, it means it's a walled square, meaning you cannot go there. It is guaranteed that 1, 1 and h, w are empty squares. The arrow will start from square 1, 1, which is the top left, and reach h, w, bottom right, by repeatedly moving right or down to an adjacent empty square. It goes either right or down, and it goes there only if it's a hash, like only if it's a dot. Sorry, if it's a hash, it cannot go there because it's a wall there. Find the number of Taros paths from square 1, 1 to h, w, and since the answer can be extremely large, print the answer modulo 10 power 9 plus 7. What are the constraints? H and w are integers. What do we have here? They're up to 1000, and each character is either a dot or a hash. And as promised in the question, 1, 1 and h, w are empty squares. Let's look at an example. Yep, I understand that. Debugger. Awesome. So what do we have here? We have a grid. We have dots and hashes. Great. Now, how does this look like visually? This is how it looks. This is how it looks, right? Awesome. Now, what are the paths that can be taken here? This is one path, this is one path, and this is one path. So there are 3 paths. All right. In this, there can't be any path. If you go down, then you cannot go down, and if you go right, you'll have to pass through this. That's why the answer is 0. Is the question clear? Is the question clear? Is the question clear? So what the question says is, you're given a grid of n by m. N by m, say you're given 3 by 4. By 4. Awesome. Now, some cells are blocked. Some cells are blocked. For example, this or this or this. Now you're over here. You need to start destination. This is your destination. It's guaranteed that those cells are empty. Yes, Aniket. Yep. Looks like the DP series has been doing good to you. All right. So we can either go here, like, what are the number of paths for this? We can go here, or we can go here. So the answer for this is 2. But what is the answer? You can do DFS here. I mean, it would be nearly same as DP. What if this x was in there? Then we could have gone here. Then we could have gone here. Then we could have gone here. We could have gone here, here, and there'll be a lot of ways basically. And it's impossible to enumerate all of them because that would be exponential, and I'll tell you why. So how do we solve this problem? First of all, if there are any doubts in this problem, please let me know in the live chat. So what do we have here? So first, the problem is to calculate the number of paths. So let's first look at a few observations. Say there were no walls at all, no walls. It's only this. If you've looked at one of my previous videos, you would have known, or even if it's a high school concept as well. So you're here. What is the number of ways to reach here? For example, this is one way, this is one way, this is one way. There's so many ways, and I want you to tell me how many ways are there to reach from here to here. Number of ways. What is the answer? There are no walls at all. How many ways to reach this? I want a quick answer. People in the live chat. What is the answer for when there are no walls at all? How would you do it? Yes, debugger, that's correct. I don't want O1 space answer. I want an O1 answer. Like O1 space answer, it can take off and time to compute. Yeah. So the answer for this would simply be, say this is n, this is m. The answer for this would simply be m plus n minus 2c m minus 1, which is equal to m plus n minus 2 factorial by m minus 1 factorial into n minus 1 factorial. Alright, now let's look at why this is happening, why this is the case. Let's look at why this is the case. I'm just looking at a special case, but like this might not necessarily be useful for the solution. Alright. Let me erase this. Oops, one second. Awesome. Let's look at why that happens. So when you need to go down, like the total, like every path corresponds to number of writes and number of downs, right? Like if you've looked at one of my previous videos on combinatorics, you can see that I've explained this problem, but I'll just revise this problem quickly here. Every path consists of downs and writes. So you can write them as, for example, this path is basically 2 downs and 1, 2, 3, 4 writes. D. This path is basically 2 writes, 1 down, 2 writes, 1 down. Alright. Any path you take this path, that's basically R, 1D, 1 down, and then 3 writes again, and another down, right? So on. So each path consists, but if you look closely, each path consists of just 2 Ds and 4 Rs. In this 2 Ds and 4 Rs. So no matter what you do when you reach the end, you must have taken 2 downs and 4 writes. Correct? 2 downs and 4 writes. So this is 0, 0, and this is essentially 1, 2, 3, 4. 1, 2, 4, 2, right? So you must have taken 4 writes, and 2 downs. And no matter how you go, 4 writes, you can go like this as well. This is also a condition. And every path would have only exactly 4 writes and 2 downs. Similarly, every string with 4 writes and 2 downs will lead to the cell, like, which means the number of strings with 4 writes and 2 downs, with exactly 4 writes and exactly 2 downs, and only that, would be equal to the number of paths from here to here, right? For example, you take any string, R, D, D, R, R, R. It would simply be R, D, D, R, 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 right? So every string is going to correspond to a path, and every path is going to correspond to the string, which means the number of strings is equal to the number of paths, right? So how many strings do we have here? We have this, the length of the string is 6, and we need to place 2 Ds and 4 Rs. How many number of ways to do that? Can someone tell me in the live chat? I have a string of length 6, and you need to find the number of strings with 2 Ds and 4 Rs. What's the number of ways? I want you to tell me. Number of possible strings. For example, this is 1 string, this is 1 string, so on. Yes, exactly. How many 4 Rs and 2 Ds can arrange within themselves to form a string of length 6? How would you do this? How would you do this? What's the answer for this? Can someone tell me? Yes, exactly. 6 choose 4, which means this is equal to, we can either choose, yeah, you have 6 boxes. We can choose to put in 2 R's in any of the 6 boxes, 2 D's in any of the 6 boxes, and put 4 in the D's in the remaining, or choose 4 boxes and put D in the remaining. Either of them works. The answer is 6 choose 4, which is also equal to 6 choose 2. Like choosing 4 boxes is same as choosing 2 boxes, right? Because you're choosing which other not to choose, right? So it's the same thing. So for the answer of n comma n, 0 comma 0 to m comma n would be m plus n, choose n. If it's 1 comma 1 to m comma n, it would simply be m plus n minus 2, choose n minus 1. It's simply, you just need to know how many rights and how many downs to calculate, okay? Awesome. Okay, I'll just give a tinier puzzle. Another puzzle. So you have another grid, a big grid now. Now you're right here right now. You need to reach here. Now say there is only one blocker. What would be the answer for this? What would be the answer for this? What would be the number of paths to reach from starting to the destination? Note that I need the answer in not a DP, not a DP solution. So DP solution had constraints 1000, but what I'm teaching you, like the tiny variations I'm teaching you, has constraints up to like 10 power 6, n equals 10 power 6. And n is up to 10 power 6. I'll get to the actual crux of the problem once I'm done with these variations. So here it's 0 comma 0. I want to go to 0, 1, 2, 3, 4, 5, 6. 1, 1, 2, 3, 4, 5. 6 comma 5. But it should not, but this is the only blocked square. If the blocked square wasn't there, my answer would have simply been 5 plus 6, choose 5. Now there's a blocked square. So now I'll have a smaller answer. And that answer, can anyone tell me what the answer would be? I need to subtract something. Exactly, Aniket got it exactly correct. We have to reduce all the paths containing this. It's like you're calculating the total number of paths, but you're removing all the paths that pass from this. And what would be the number of paths that pass from this minus number of paths passing through? What is this value? Oh, this is actually 6 comma 6, is it? Oh, 6 comma 5, okay. Now this value is basically 4 comma 1, passing through 4 comma 1. Right. Awesome. How many paths? Like, there'll be a lot of paths. This is one path, this is one path. But there'll be, all these paths should be counted. But this path should not be counted, for example. This path should not be counted. So how does a bad path look? Bad path looks something like, first you reach this cell and then you reach this cell. Or like you can go like this, you can go like this. So any way that reaches this cell, and from here you do another path to this cell, right? Right. Isn't it? So basically the number of paths from S to D, source to destination, passing through this point would first be, let's call this destination as W, the wall as W, would be number of paths from S to W multiplied by number of paths from W to D. Because each path from here and each path from here will give you a solution. So the number of total paths would be the number of paths from S to W multiplied by, you can independently do another path from W to D. Right. All right. How many paths are there from S to W? Can someone tell me? How many paths are there from S to W? Exactly. Hiran has got it right here. So S to W is basically, oh, hi Hiran. S to W is basically 0, 0 to 4, 1, and the answer for this would simply be, oh, this is 4, 2, sorry, 4, 2. My bad, I'm sorry. 4, 2. The S to W would simply be 4 plus 2, 4 plus 2, choose 4, or 4 plus 2, choose 2. And the number of paths from W to D would simply be how much it's basically the difference between those coordinates, right? It's basically you're traveling 2 downs and 3 rights. So the answer for that would be multiplied by 5, choose 2. Right. So the answer for this is simply 11, choose 5 minus 6, choose 4 into 5, choose 2. This would be our answer. The number of paths from here to here not passing through this. If it's passing through this, it would be this. Not passing through these means total paths minus the number of passing through. Is that clear? Any doubts with the solution so far? Any doubts with the solution? Any doubts with the solution? Is there any part you'd want me to re-explain? Is there any part you'd want me to re-explain? Yes, clear. Awesome. Awesome. All right. Now, let's look at the actual problem. All these problems were just like basic grid problems that I just wanted to cover. They might not be directly related to the problem, but they're still grid problems. So, okay. Awesome. Now, the actual problem. First of all, assume again, there are no walls. How would you do it in a dynamic programming approach? Someone already mentioned it before. How would you do it in a dynamic programming approach? So you have these cells. You're over here and you need to go here. So 0, 0, and you want to go to 4, 3. Like it's, you can write as 3, 4 as well, depending on your convention. Awesome. Now, answer of n, answer of 4, 3. From 4, 3 can either come from here and or here. So number of paths from 4, 3 would simply be number of paths of from 4, 2. This is 4, 2. Or you can come from the top, which is simply answer of 3, 3. Right. I don't know, like just simply stating BFS might not like, I mean, BFS will work if you're like storing the answers for the children. Like for example, if you store the answer for this and this, and then return it, it will work. Like, yeah. I mean, it depends on how you use it, right? Yeah. And similarly, answer 4, 2, you can go right, you can go one left and you can go one or one top. So that if you go one left, it would be answer of 4, 1 plus answer of what would happen if you go one up? The answer would simply be, I guess, how much? Oh yeah, the answer would be answer of 3, 2. Similarly, answer of 3, 3 would be answer of 2 comma 3 plus answer of 3 comma 2. So answer of m comma n would be answer of m minus 1. Similarly, like you can go one left or you can go one up. Like how you reached your, there are two possible values. You could have reached the destination from the left or from the top, right? So answer of m comma n simply answer of m minus 1 comma n plus answer of m comma n minus 1. That is simply it. All right. For example, you can compare this from bottom up approach either as well. For example, answer. Okay, wait. I'll just erase this once. So you have we know that everything in this row would be 1 because there's only one way to go from start to everything in this row. Similarly, this column 1. Awesome. Now we have filled that. Now the answer for this row, it's this row, this one plus this one, that's 2. This 1 plus 2, 3. This is 1 plus 3, 4. This 1 plus 4, 5. Awesome. Now, what would be the value of this? 2 plus 1, 3. Value of this, 3 plus 3, 6. This 10. 10 plus 5, 15. You can come from the top or from the right. Let's fill this first and look at how it looks like. 1 plus 3, 4. 4 plus 6, 10. 10 plus 10, 20. 20 plus 15, 35. 1 plus 4, 5. 5 plus 10, 15. 15 plus 20, 35. 35 plus 35, 70. Now let's just rotate it and look at it. Like if you look at it like this, like it's basically 1, 1, 1, 1, 1. 1, 2, 3, 4, 5. 1, 1, 1. 2, 3, sorry. 3, 4, 5. 6, 10, 10. 35. 20, 35. What did I miss? Oh, sorry, there's a 15 there. 15 here, 15 here, 20 here, 35, 35, 70. If you look at this, like, isn't this Pascal's triangle? And this keeps extending as you move on. This is the Pascal's triangle, right? Can you see that? Like, I mean, it is supposed to be because like we just computed that m comma nth is going to be the ith binomial coefficient, right? So can you see that how this becomes the Pascal's triangle? And if we keep on extending, that's how it's going to look. One again, one. This is going to be 1. This is going to be 1, and then underneath would be 6, and so on. You can keep writing it forward. Is that clear? Like, yes, yeah. That's basically the Pascal's triangle here. Awesome. All right. Now, is everyone clear with the recursive approach? Let's write Pascal's triangle here. For those who don't know what the Pascal's triangle is, I really suggest you to either watch my binomial like combinatorics video, or you can either Google it as well. Like you can search it on. Yeah, it's really popular. So can we do it like this? As we discussed before, dpij says how many ways I can reach to I comma j to 0 comma 0. Yes, you can do it exactly like that. That's what I'm going to show. dpij storing. Yeah. So basically dp I comma j is equal to dp I minus 1 comma j plus dp I comma j minus 1. That's exactly the recursive formula. And from there you just compute everything from you can call the recursive function directly. You ask what the answer for this is, then the answer will call this, and so on. Yes, that's correct too. I will show it to you. Yes, Aniket, that's correct. Yeah. All right. Now that there are blockers, How would you go about it? How would you go about it if there are blockers? Now that there are blockers, it's going to be slightly tricky. It's going to be slightly tricky, but not very tricky either. For example, you're here right now. Now you want to go here. There are blockers here, blockers here. There are blockers here as well. There are blockers over here as well. And here. Oh, that'll reduce the number of paths too many. Okay. The blockers here. Awesome. Now you want to calculate the answer for this. The answer for this is basically this plus this. The answer for this is 0. So the answer for this is basically answer for this and this, but when you return the answer for this, this cell, the blockaded cell, will return 0 instead of the actual number. So if it's a blockaded cell, dpij is 0. If I comma j is a wall, dp I comma j equals 0, else dp I comma j equals dp I minus 1 comma j plus dp I comma j minus 1. That's it. We don't have to take care, like if I comma j is not a wall, we don't have to take care if now you might ask, what if I minus 1 comma j is a wall, or I comma j minus 1 is a wall? We don't care. Why? Because if it was a wall, then it would have been marked 0 already, so it's not going to contribute to your answer anyway. So let it be 0. Like let it be a wall. So what? This will return 0 anyway if it's a wall, right? So we don't need to explicitly account. I mean, we can write a case like if I minus 1j is a wall, let's not include it, but that's unnecessary. Anyway, if I comma j is a wall, dpij is 0. Otherwise, dpij is just you go up, or you come from the top, or you come from the left. So there are two options. It's as simple as that. So let's get started without any delay. Oopsie. Where's my sublime text, man? Okay, yeah, it's here. Type this code. One sec. Just give me a minute. I'll just set it up once and I'll get back to you on that. Let's get a coding then. Let me know if you have any doubts so far. All right, let's get started coding. Awesome. So what do we have our input as? What do we have our input? Let's declare mod equals 189 plus 7, right? All right, let's declare what the mod is. Fine. Now, what is our input here? Input is n comma m, right? Input is n comma m, int n comma m, scene n m. Now we have n rows. Let's declare a string of length n. Let's declare n strings, each one of length m. But we don't need to declare it since you're taking the input directly, right? For int I equals 0, I less than n, I plus plus, scene a of I. Now, Let's declare this on the top. We can pass it by reference as well, but I'll just, this is a sequential code, which it's okay. Like, let's not focus too much on. Yeah. Now we can just see out solve of n comma m. That's what we're going to do. Or rather, we solve n comma m. Awesome. Now, int solve, rather long, ll solve int n int m. If n less than 0 or m less than 0, return 0. If a of n m equals a blockade, return 0. If n equals 0, these are the base cases, or m equals 0, return 1. We don't need to write this, it's never going to go there, right? So we can write it, but we don't need to. Return solve of n minus 1 comma m plus solve of n comma m minus 1. That's it. That's the solution. So solve of n comma m is basically, if it's a hash, then return 0. If it's one of the borders, like now it's not a hash, it's guaranteed that it's not a hash, it's empty, it's a hash, or rather I'll call it a wall, so that to open no line of misinterpretation. All right, it's empty. Now if it's empty, now if it's on one of the borders, your answer is going to be 1. Otherwise, it would be either you're coming from the top or you're coming from the left, which means solve n minus 1m plus solve n m minus 1. All right. Awesome. Is this clear? First of all, is this clear? Is this clear? Any doubts with this? Any doubts with this part so far? Is there any line you want me to explain? Awesome. Okay. All right. But what is the complexity of this? Can someone tell me what the complexity of this is? What is the complexity of this? Complexity. What is the complexity? Note that we are not storing anything here. What would be the complexity of this? What would be the complexity? Right, it's going to be exponential. For n comma m, the complexity would simply be the maximum answer of n comma m, which is basically m plus n. Right. And this is approximately like 2, this could be, it's not approximately, it's at least 2 to the power n by 2 plus n by 2. Wait, it depends on actually, wait one sec. Like if m equals n, this would be 2n cn. 2n choose n. If m equals n, this is going to be 2n choose n. And this is like, this is at least 2 power n if you think about it, like if you write it down a bit and if you cancel out terms, you'll see that this is at least 2 power n. That's how it's exponential. It's not 2 power n plus m, it's going to be less than 2 power n plus m. If n is nearly m, it's going to be 2 power n plus m by 2. It's going to be way greater than that, but yeah. Awesome. Let's look at how to do it efficiently. let's simply declare a DP array, as we always do. Initialize all of them to -1. DP of n, m equals return. Remember we need to take the mod as well, right? Return DP n m. Now, if DP n m is not equal to -1, that means it's already computed. Because we initialize it to -1, it's already computed. Now you return it to return this value if it's already computed. So this means it's already computed. Already computed. For computing n comma m for the first time. Now, if it's not a wall, it's empty. If it's really empty, like it's not a wall anymore right now, that cell is empty. Now you're going down. This is the border cell on the edge of the board, closer to the origin. Like there are multiple edges, but this is the one on the one closer to the origin, right? Awesome. All right, is this clear? Any doubts with this? Any doubts? DP complexity would be O of m into n, correct? The time complexity, it's hard to do it under m command because there are walls everywhere. There can be walls like in a lot of places, and there can be up to m into n walls, and it's not possible to like it's pretty hard to not go up to m command because you need to know where walls are there everywhere, right? So yeah, is this clear? Is this clear? We just introduce memorization, that's it. Any doubts with this? Awesome. Awesome. Now let's convert it to iterative. Let's convert it to just iterative. This is the recursive way of doing it. Let's make it iterative. How do we do iterative? For int I equals 0 less than equal to oh wait, one sec. I probably made a tiny mistake. It starts from 1, 1, right? So just a tiny correction that this is n equals 1 or m equals 1 because here it'll start from 1, 1. That means row 1 and column 1 are your what do you mean? They're your actual numbers, or then this would be n minus 1, m minus 1 because all of them are 1 indexed, right? That's why. Awesome. So this is your solution. Like it's almost same. Like you just need to. These are minor details which you need to get right. All right. Awesome. Now, how do you do it iteratively? It's the exact same as recursive, but like we just need to loop on our own. For int I equals row equals 1, row less than equal to n, row plus plus. Now what? For int call equals 1, call less than equal to n, m columns, column plus plus. If row equals 1, first of all, the very first condition, which is what this, if a of row call minus 1 equals hash, meaning dp row call equals 0, else If row equals 1 or column equals 1, the answer is going to be 1. This is the real base case. Return dp row col equals 1. Else, the other one, the last case would be if it's a general square inside the grid. Row col equals dp row col minus 1 plus dp row minus 1. So this is if you're coming from one row above, sorry, one col, like if you're coming from the left, coming from left plus coming from right. You need to take the modulo of the whole thing because it can get really large. And in the end, that's it. That's simply it. Like cout dp, how many rows are there? N rows are there and m columns are there. That is simply it. Yes, I did take the array with size. I mean, you don't need to take array with size n plus 1 because they've still specified n rows itself, just that their convention is one indexed. There's still n rows, 1 to n. Is that clear? Any doubts with this so far? Any doubts with the solution so far? Any doubts? Is there anything you'd like me to re-explain? Is any of this unclear? Hiron is asking, we have to iterate from row equals n, row less than 1, row minus. No, why? Because like if you iterate from row equals n, and this is a bottom-up approach, this is a top-to-bottom approach. Like you don't know the answer for the top, so you're computing the answers from the bottom. But here like this is a recursive function called like n comma m is asking what the answer of n minus 1 comma m and what the answer is for n comma m minus 1. But here, when you're computing, like you can't directly go from nth row and ask what my answer of n minus 1 row is, because I'm not calling myself again. I wouldn't know the answer without actually computing it before, right? So this way, it first computes for the first row, and then you can compute for the first row, and then like you can compute for row I comma j only if you know the answers for all I minus 1 and all the rectangle above it, right? Right. So Crimsonite, so wait, I'll just answer Hiran's question first. So yeah, like if you can't just iterate from row equals n, because what happens then is like you simply don't know what the lower answers are, like to compute that answer. You could have in the function, when you're writing a function, a recursive function, we could have done that because we can directly call the same function again. Here you don't have that like flexibility, right? You just need to you don't know the answers for the lower row comma column. And Crimsonite, I would suggest, like if you don't know, if you really want to convert it into a tabular DP, at least for 2D, a good practice might be to maybe just draw the table sometimes. But like your first step of visualization should not be a table. It should be a if you really want to get concepts clear, it should be of states. Like row comma column is a state, DP state. In this case, you can look at it as a table. and then figure out what cells in the table are base cases and what are not, and what are using recursive calls. Yes, line number 38. Okay, that's when it's a wall. It's a wall. So answer. So paths. Is this clear? Is this clear? In line 38, why are we taking? No, okay. It's not okay. So here when I write, okay, this is not the top left. This is not the top left. Row 1 at column 1 in A is A of row minus 1 and column minus 1. So Flamboyds, I'm in Dublin right now. I was in India a couple of months ago. So Aniket, so row and column is one index, whereas the vector A is 0 indexed. That's a small catch, but like for example, you can make this 0 to n. You can perfectly make this 0 to n, and it'll still work. 0. If you really want to make it 0, I just need to remove this and add dp n minus 1. You'll have the same answer. And here I just need to update the border cases. Row equals 0, column equals 0. No, this is the so we don't need to take row minus 1 column and row column minus 1, because if a row and column is 0, like dpij is defined as dpij is 0 if my current wall is 0. Now if my upper wall, if I'm empty, and if my upper cell is a wall, and if my left cell is a wall, this will make it 0 automatically, right? Because if my upper cell is a wall, this would be 0. Sorry, if my upper cell is wall, this would be 0. If my left cell is a wall, this would be 0. So 0 plus 0. My current wall would be 0 automatically. Alright. Hope that's clear. Is that clear? Any doubts? Do you all have any doubts? Yes. This is clear? Any doubts so far? Awesome. Now what are we going to do? Now let's look at the space complexity of this is O of n into m. Can we do better? Can we do better? Like extra space. Of course, you need to take in the input. So as in, the input space can be taken row by row, and okay. All right, forget that. Can we reduce the extra space to O of m or O of n? O of n or O of m. Can we do that? Can we? Yes, turns out we can. So look here, look at what we're doing here. Row equals 0, row from column equals row equals 0 to row equals n, column equals 0, column less than n. As we're taking only the previous row, we can take 2 on DRS. Exactly. So for DP of row, we just need DP of row, which is okay, which we are already having, and DP of row minus 1. You need the previous row for this. You need the previous row, right? That's why the optimization comes in. That's why the optimization comes in. So we just declare 2 rows. Previous of what would be the length of it? M plus 1. You can just write it as m plus 1. Current m plus 1. Now, wherever there is DP of row, I'm replacing DP of row with current, and DP of column row minus 1 as previous. Now, after I'm done with computing the current thing, I need to just write previous equals current, right? And DP of n minus 1 is just like previous or current. You can write anything because in the end both will be equal. Current. That is it. That is it. Wherever there is, okay, wait. Yeah. This would be it. So you either go from the current, in the current row, you either go left, or in the previous row, you stay in the same column that is coming from the top. Is that clear? Is that clear? So what would be the space complexity of this? O of space complexity is simply storing 2 arrays of size m plus 1 and m plus 1. The space complexity of this is O of m. We can reduce it to from m to minimum of n comma m. How? We can, if n is less than m, we can just take the reflection of the grid a of ij equals a of ji, and you can do that thing. All right, let's not go there. That's not required. Like, I mean, yeah. So here's this. So is this clear? Any doubts with this? Was this clear? Do you have any doubts in the solution? In the next class, I'll be teaching some probability as well, very basic probability problems on coins and so on. No doubts? Awesome. 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 Clear? All right. All right then. If this is clear, then I guess, can we, I'll just introduce another tiny optimization, please allow me to. So, note that we can, for a row, what matters is only if the current value is, current row's column is a hash or not. So what we're going to do here is, so we can take each row input one by one. So we don't need an n by m string. Like the complexity is this. Okay, wait, I declare this. This string is that this is n. So basically, after taking all the inputs, A is equal to, A would be a 2D string matrix, right? 2D matrix, m by n. Turns out we can just store the current row and then compute it as we go on the fly. I'll tell you what I mean by this. So I'm doing for int I equals 0, I equals n, I less than a c in a, right? Instead, if I just take the string here, string s, c in s, and forget all of this. Now instead of a of row column, I just check if the current column is a hash or not. That's it. So like for each row, I'm taking the input first. Now after taking the input for this row, then I'm computing the answers. So for each row, I'm taking this input. Now I'm checking if like s of call is simply, it's the same as a of row call, right? For each row, I'm taking the string. Instead of writing a of row call, I'm taking the string at each place. So the time complexity, space complexity would simply be O of n now. O of m. This is clear. Is this clear? Since I'm taking the string for each row at once, and I don't care what my previous strings are. That's it. And since I don't care, like I don't need to store them either, and I can just compute the, like, as in take the strings as we go. Is this clear? Any doubts with this? Do you want me to re-explain any part of it? Aniket says, so we can take a single input and we can calculate the necessary operations, and we don't need to consider the input array. Yes, we don't need to, we take the input, once we used it, we throw it away, and so on. Is that clear? Yes, complexity, time complexity overall will be OM, not just the extra space. The overall space will be OM. You might say, but you need the whole string array, right? Now you might think like, I need the whole matrix, but how did I just get away with storing only one row? Yeah, you need the whole matrix, but when you take the input for one row, you don't need what's there in the previous row, so you just like throw it away. Like you take the input and at this point you throw it away. Like after the loop ends, like S is free, right? So after the we're getting a complete string input. There's no outer bound. Grimson asks if there's going to be any outer bound. No, the length of the string is going to be m. That's promised in the question. And then we're checking for each column. Yeah. This is clear. Any doubts? So what do we do here? So first we looked at several variations of the grid problem, like several special cases of the grid problem, and then we approach the grid problem. Like you don't need the variations to actually solve the grid problem, just a dynamic programming approach. Now what do we do? First we saw like if there are no walls at all. Now then we saw what if there is one wall, and then we saw that if there are many walls, doing it like how we did for the single wall would be a little more complicated. Right. Then what did we get? Yeah, would be a little more complicated. After which we saw like how can we reduce the solution for n comma m to a smaller n comma m, and we did that too. And it's and after doing that, it doesn't end there. Like you can still submit the problem and say, hey, I'm done with it. But then we try to reduce the space complexity as well. We try to reduce it from the top, the recursive approach to the bottom-up iterative approach, which is usually faster. After which we try to eliminate extra space from O of n into m to O of m. by figuring that the previous DP rows, you just need the previous DP row to compute what the current DP row is. That's DP row. For DP row, we just need DP row minus 1. And we don't need the other one. So we just store the current and the previous DPs. And then in the end, just to top it off, like we didn't need the whole input. We just needed one row. And that's what we took. And then we discarded the rest. So the space complexity would be O of M. Yeah. Is that clear? Any doubts? Any doubts? Do you want me to re-explain some part of this? Or any part of this? I'd be happy to re-explain. Is this clear? Any doubts? Awesome, awesome. Awesome, people. Then in that case, I guess we can end this class in that case. Then do attend my next class. I'll be speaking about solving the problem coins in Atcoder. The topics would be probability and dynamic programming, and I would be covering several variations of coin problems as well. So please come there. Thank you. And okay, wait, before that, don't forget to join this Telegram channel for live updates. And if you haven't liked it already, and if you think the video was useful to you, please do drop a like so I know it was. And if you didn't like it, or if you think there can be something that I can improve, please let me know in the comments or the live chat. And don't forget to subscribe if you really want to see more of this content and don't want to miss out on any of this content. And don't forget to share it with your friends if they just started competitive programming. Chances are it's going to be useful to them if they're a beginner. All right. See you in the next class.